Okay, chapter 5, computers and computer architecture. So it's a very short class and very short chapter. Just a small little bit of discussion about computer architecture. So we have logic. Yes. I mean, I can make it 46 if you want. So I'll make the change before I sit down to grade. Okay, so saying chapter 5. All right, so we looked at logic circuits so far, right? Logic circuits, and then we use them to implement our mathematical functions. Now we see how these digital circuits can be organized. I mean, as a hardware can be organized to form computers. So computer architecture and organization is what we'll talk about a little bit here. All right, computer architecture comprises of a central processing unit. The central processing unit itself comprises of something known as ALU, arithmetic logic unit. And the ALU is basically a circuit created from logic gates, flip-flops, to create or to implement arithmetic functions, mathematical functions. Okay, so CPU comprises of an ALU, and then there's a control unit that controls everything, right? And the CPU interfaces with external peripherals, and input devices. So here you have input devices, you'll have your keyboard, your mice, touchscreens. Right, peripherals. And then as it works with the peripherals and the input devices, it needs to store and retrieve data. Hence, we need memory. As memory, as you'll see in the next couple of slides, comprises of many different kinds, but there are two broad categories. Okay, so all of this interfacing takes place via a bus, and a bus is nothing but a collection of wires. Since all of the information is moving together on all those wires in parallel form, it's known as a bus. So remember, external peripherals can be connected via parallel or via serial connections, but internally, it's all parallel connections. If you have a 4-bit processor, you need 4 wires. It's a 4-bit bus, but you can only work with 4 bits at a time. And then you had 8-bit processors, you had 16-bit processors, then 32, and of course 64-bit processors are now the consumer grade standard, which require 64 wires to move data between the CPU and the associated circuitry. Okay. A CPU interfaces with numerous several components. So here's the CPU, here's the main CPU bus. It interfaces with memory. It interfaces with AD converters, DA converters, and then external sensors and peripherals. Memory is of two kinds, volatile and non-volatile. Volatile simply means that power must be continuously supplied to the memory circuitry in order for the storage to remain present. As soon as the power is turned off or power is shut off, the memory is wiped clear. Okay. Okay, volatile memory, power must be supplied in order for the data to be stored. Non-volatile memory, power is not required to retain the information. Okay. The nomenclature of volatile and non-volatile memory, which is RAM and ROM, is kind of a misnomer. Okay. ROM, as the name suggests, is non-volatile. It stands for read-only memory. Okay, so as the name suggests, you can read from it, you cannot program it. But read-only also indicates that the memory is stored in the chip itself. Okay, but RAM, however, does not stand for read-write or volatile or non-volatile. RAM stands for random access memory. It actually has to do with the description. It actually describes the manner in which the memory, the stored memory, is accessed. Okay, so typically memory would be accessed in a sequence or in parallel, right? So if you have an 8-bit register, it stores 8 data bits. If it's a serial fashion, the data comes out bit by bit. A random access, if you will, think of it as a matrix. Okay, let's say you have a 64-bit system, so you have a 64 by 64 X and Y times a matrix. So you have 64 times 64 bits of storage possible. And then if you wish to access the memory, you can randomly go in and access any data information that you want. Hence the name random access memory. So it's much faster. Okay, it's much faster. So again, RAM and ROM, the nomenclature comes from two different kinds of setup. The read-only memory is just to describe how the memory is actually read or programmed into the system. RAM indicates how the memory is accessed, not the way it is stored in the system. Anyway, when memory was first created, the first early devices, that's what it meant. Okay, RAM is further divided into static and dynamic, hence SRAM and DRAM. And ROM chips, there are multiple different kinds of ROMs. Depending on the application, you do not need to program that ROM. The programming is done during manufacturing itself, meaning you program the chip in your fabrication process. It's only designed to do a few things. If you create, for instance, if you take multiple transistors and you create a circuit, you already programmed that circuit into the fabrication process to actually function as a switch, maybe to function as an amplifier. Does that make sense? Right? So the function is itself designed into the circuit. Hence, read-only memory. Then they came up with programmable read-only memory, or PROM, meaning the consumer could buy the ROM and program it just once. Then they came up with erasable ROM. You could erase the memory by shining UV light onto the chip, and you could erase it and program it again. And then came the EEPROM. It's not the PROM for EE department. The EEPROM stands for electrically erasable programmable read-only memory. Meaning if there was an application where you need to continuously electrically erase and program the ROM chip, that would be the case. ROM chips are still used. When you boot up your computer, the main board and the CPU needs to know what instructions it needs to execute. And so you store those basic functions in a ROM chip. That is known as the firmware. That program is known as the firmware of that chip. And the firmware is so called because it's hardwired. It's not hardware. It's firmly stored in there. Hence, they came up with the term firmware. So there's hardware. Obviously, hardware refers to the physical components. You cannot modify the components once they're manufactured. Hence, hardware. Then there's software, which is the soft program which you can change at will. And then firmware is something in the middle. Okay. So firmware is something that is stored in these ROM chips. And then the CPUs also interface with something known as ADCs and DACs. ADC stands for analog to digital converters, and DACs or DACs are standing for digital to analog converters. Peripherals like sensors capture the signals. The signals can be any physical quantity, which are then converted into electrical signals. These electrical signals would be analog in nature. Then these analog signals are converted into digital signals. The computers or the computer's CPU would take these digital signals, run some processing on it, and then the output is sent back externally if needed. Those digital signals then are converted back into analog signals. As an example, this microphone is capturing the sound of my voice, right? So it's capturing the sound signals. This microphone converts the sound signals into electrical signals. Those electrical signals are analog in nature. Those analog signals, when they reach the computer, are converted into digital signals, processed digitally, and then it's sent back out. When it's sent back out, that digital signal gets converted into an analog signal, transmitted via the internet. And then, of course, if I was running a audio test in here, that analog signal gets converted. It's sent out, and it's sent out to the speaker, and that electrical signal is then converted into sound waves, right? So you need an analog to digital converter, and you also need a digital to analog converter at the output side. Some other examples of ADCs or sensors would be the camera. The camera sensor captures the light. Thermostat captures the physical quantity temperature. There could also be pressure sensors, humidity sensors. These are all capable of capturing any physical quantity and converting it into electrical signals. And then those electrical signals, again, get converted into digital signals for processing. All right, so that's CPU. Again, for computer systems, if we wish to interface with the computer system, we need to tell it what to do. So in order to tell it what to do, we need to use a language. The language of machines is basically known as machine language. Machines do not understand A, B, C, D, or 0 through 9, right? It only understands the presence or absence of a voltage. So we need to key in something. We need to enter some sort of input that tells it, that's what I want you to do. That's known as machine language. And then above it is assembly language. That there's an assembler that allows the machine to understand what we are trying to tell it to do. So that's the lowest form of language when it comes to machines, right? Assembly language or machine language. The highest level or higher level languages is basically what we humans use. Those are programming languages, right? So there's an interface or a compiler that comes between high level languages like, let's say, for C or C++ or Python, for instance. Even as non-CS majors, electrical engineers, mechanical engineers, industrial, biomedical, it is now an essential skill to have some sort of programming knowledge, whether it's C or Python or MATLAB. These are all very valuable skills for you to know as an engineer. Okay. You might not be sitting there doing programming all the time, but as a mechanical engineer or as an industrial engineer, you would still come across a system, mechanical or industrial system, that has an embedded computer in it. And that embedded computer would have some programming, maybe some assembly language programming, or some C or Python programming in there. So higher level languages would be C, C++, lower level would be machine or assembly language. Assembly language, that's something I studied more than 30 years ago. And then how does the CPU know which system it needs to pay attention to? That is handled by something known as interrupts or polling. Polling is basically a CPU or a processor monitors the sensors that are connected to it in a sequence. Okay. It continuously monitors or polls the sensors. Is there any new data coming in? Is there something else that needs my attention? That's what polling is. Obviously, that's a waste of a time if you have like a complex computer system. And so a much better way to do that is by interrupts. Interrupts is basically a CPU, it's executing its task, and then any peripheral, any sensor, or any other device connected to the CPU can interrupt the CPU and tell it, hey, this is something you need to pay attention to. So it might be computing something, and then a print command could come through where it says, okay, I need this to be printed right now. And so the CPU is interrupted by its current function, and thus it is able to handle all these requests. Okay, and so that's interrupts. Let's see how much time, 51. All right, so that's a CPU, computer. Then there is a microcontroller. Microcontroller, unlike a CPU, has a CPU, but the processor integrates some memory and some storage inside it. Okay, even some I/O addressing lines inside it. And so microcontroller is a scaled down version of a CPU, but it integrates a bit more than a CPU inside it. And microcontrollers are designed for one specific function. So if you have a microcontroller, you can program it to do one thing and one thing only. And these are useful for single function appliances. For example, a microwave, dishwasher, washer dryers, refrigerator, perhaps. Okay. Those are all appliances in the residence, consumer appliances, where microcontrollers would be useful. If you have a machine in a machine shop, you might have a microcontroller to control the functions of those devices. So that's where we would use microcontrollers. One of the most popular microcontrollers right now, well, not right now, as a student that you can use, is the AT328. This is a 8-bit microcontroller with a reduced instruction set. Hence, it is also known as a RISC, RISC, reduced instruction set computer. It has bidirectional I/O ports, meaning it can receive data and it can also send out data. And there are connections for ground and power supplies that can provide. How many of you have used this? I'm sure some of you have. How many of you have worked with an Arduino? The Arduino is powered by a 328 chip. So if you look at an Arduino board, you see this chip right there? That's 28-pin chip is the AT328. All right, so Arduino project was created by 2 or 3 Italian guys. And as with most creative ideas, or a few pitchers of beer at a pub. And they decided, well, not decided, but they were trying to brainstorm some ideas about how to bring hardware and software prototyping to the masses, like in an easy way for enthusiasts and students to learn, as a way to build interest, right, in software and hardware programming. And so it was a open source hardware and software prototype. Anybody can buy this microcontroller, interface with some sensors, write a short program, and tell it what to do. Okay, it's a very easy way to start learning about hardware and software prototyping. It has been around for a few years, actually several years, and there's a huge worldwide following of enthusiasts who work with Arduinos. If you have not yet worked with it, they are not very expensive. Right around the pandemic time, I think kits were available for like $30 or so. Nowadays, they might be like 40. So for 40 or 50 bucks, you can buy an entire kit that comes, it comes with the Arduino, with a breadboard, several chips, resistors, diodes, LEDs, several components, and several sensors, which you can build your own project with it. There are many programs that are already available on the internet. You can simply download it and be up and running within like 15 minutes. You can have your own temperature sensor or thermometer within up and running within 15 minutes. 15 minutes. It's that easy. So again, it has a large library of high-level functions that are available. It's an easy way to start learning about C programming. Okay, so the user programs are known as sketches. They're written in C or C++. It's a very easy way to start learning about C programming. So if that's something that piques your interest, then something to do. During the pandemic, I used the Arduino to create a hands-on lab for EE251. So students were required to buy their own Arduino kit and a handheld digital multimeter. And I created a set of experiments where they could replicate the entire 251 lab class in their own residence. So they were not just looking at simulations, they were actually doing hands-on work. One of the things we created was use the Arduino as a voltmeter, and then also use it to measure humidity and temperature. And it actually is relatively straightforward. There's a humidity and temperature sensor that comes with the kit. All we have to do is you connect the sensor to the Arduino controller, and there's a small program you write, and you just tell, okay, we have connected the sensor to pin numbers 1, 2, and 3, read the data, compile it, and then send the output to the LCD display. So if this is your kit, sensor comes in, the input comes from the sensor, the Arduino controller processes the data and sends it out to the LCD display. And the result is what we see here in the image. I have several Arduinos lying around, so I repurposed one of them to actually display this, and it's sitting on my office desk in case I need to show facilities how cold it is in my office. Anyway, so that's the Arduino. And then there's the Raspberry Pi. The Raspberry Pi is a full-blown microcomputer itself. Okay, far more than a microcontroller. So this can do high-level programming. So if this is something, again, if you wish to go down this path, it's something that you might want to look into. The Raspberry Pi and the Arduino are both very, very popular worldwide. Okay, and there are several versions of both that have come through the years, and they are now in a very advanced state. Then we have system on a chip, SoCs. SoCs basically incorporate everything. Incorporates your CPU, your memory, your storage, your graphics processors, even your wireless modems. So depending on what what capabilities you want to have in there, you can incorporate everything inside your SoC. This here shows you a SoC created by Qualcomm. These are all based on a architecture known as RISC. Let's go back here. We're almost out of time, so if you have to leave, you can leave. I'm just going to do one more thing. RISC, as I said, stands for Reduced Instruction Set Architecture. The computers basically need an instruction set which tells it what it needs to do. There are only 4 of them: Harvard, Von Neumann, x86, and ARM. x86 is basically what Intel and AMD do, and then everything else is ARM. ARM is a small, or at least was a small, British company. Stands for Advanced RISC Machines. This company, the small company, basically is what powers the world today. 99% of the architecture that is used in the world is licensed by ARM Holdings. Apple, NVIDIA, Qualcomm, Samsung, pretty much any corporation that creates their own SoC is licensing the ARM architecture. So if you wish to invest in a stock, you might want to check this out. This company is behind everything that we use nowadays. Okay. It's not easy to come up with your own instruction set. It takes years and years work. So ARM, again, as I said, in the heydays of Intel and AMD, ARM was a far smaller company, but now in these mobile computing days, it's the most popular architecture around. And ARM supplies all semiconductor companies worldwide with their own architecture. They buy the licensing and the architecture from ARM, and then they create their own circuits with it. All right, so we'll end class here today, and I will see you all on Wednesday. Going forward, we'll work with lots of circuits, circuit analysis, problem solving, problem-based learning, all the material you have done so far. Okay, so active learning. All right.